I don't know whether this is by design or pure sheer luck, but we actually have a segue here between what Jessica just presented and our next presenter, who has a long resume, but people are not the biggest consumers of energy in this country. It is, in fact, buildings are the biggest consumer of energy in this country. And for an explanation of why that is, but more importantly, on what we can do about that, please welcome Professor with the favorite name to pronounce tonight, Aimee Buccalletao.
Well, thank you. Okay, let me get set up here. All right. So when I give talks to non-architects, I find it really helpful to situate sustainable architecture and design as a universal concern. So this is going to require a little audience participation. So if you'll indulge me just for a moment, how many of you are architects? Engineers. All right, future real estate developers, keep those hands up. Hands up, hands up. Come on. All right, how many of you work inside, indoors? Okay, in buildings. All right, so we're getting there. How about where you live? In buildings? Keep those hands up. Okay, right. So we're almost at 100% now. So essentially, you know, we all work, we live, we play, we engage in the built environment every day. So in a sense, we're all complicit in this, that buildings are the largest consumer of energy, and as a consequence, energy use tied to buildings produces 40%, nearly 40% of the total carbon dioxide emissions annually in this country. And by 2025, the US Department of Energy predicts that buildings are going to be responsible for full 75% of the electricity that we use in this country. And it's not just these energy hogging commercial buildings, right? These statistics are split almost evenly between the buildings that we live in and the buildings that we work in. So when it comes to energy use in the building sector and efforts made to reduce energy and certainly greenhouse gas emissions that are tied to it, sustainable architecture really is everyone's business. And of course, architects bear an even greater responsibility for this. So this is why my research focuses on developing tools and methods and practices that are going to advance the design and execution of truly sustainable buildings. And there are a lot of people that are looking at and working on this building energy problem. And most of you have probably heard of the LEED system, right? So this is probably the most well-known, at least in this country, system for influencing sustainable design. And like most efforts and policy initiatives that are related to this building energy use problem, LEED's looking primarily at how buildings use energy in operations. So energy towards heating, cooling, anybody else feeling the chill in here tonight? And lighting, right? So we are focused primarily today in making our buildings operate in a predictable way and optimizing their use of energy in operation. Or something which is most known today as trying to achieve net zero energy use in the operating phase of a building. So there's a lot of research and development that is being directed towards advancing technology, coming up with new technologies to help us achieve these energy gains in operating our buildings. But if we're going to understand the full potential of these technologies, sort of the true benefit of these technologies, we really need to understand the broader impact of these technologies when they are deployed at the building scale. So one of the ways that we do this is through life cycle assessment. And for some of you who won't know what life cycle assessment is, I like to use this helpful little example. Okay, so when you're weighing whether it's more environmentally responsible to read your favorite paperback novel or to download it on your handy e-reader or your Kindle or whatever it may be, life cycle analysis actually comes up with a pretty surprising answer to that question, that question here. So according to an LCA study that was published in the New York Times in 2004, one e-reader requires the extraction of 33 pounds of minerals, and that includes trace amounts of exotic metals, and it also requires 79 gallons of water to produce. Whereas the traditional average paperback book, which is made out of recycled paper, consumes only about 2/3 of a pound of minerals and only takes about 2 gallons of water to produce. Now, manufacturing a single electronic device like this one involves 100 kilowatt hours of fossil fuels and generates about 66 pounds of CO2. And on the other hand, the manufacturing process for this traditional paperback requires just 2 kilowatt hours and is a process that expends 100 times less CO2. All right, so what is the bottom line here? If you include the impacts related to disposal, the ratio of impact is one e-reader versus a paperback book is about 40 on the low end, 40 books to 1 on the low end, and that's just looking at fossil fuel and water and mineral consumption, and 100 books on the other end, and that's including some of the global warming potential and health impacts. So we're just talking about a small device here, right? And it's admittedly a very helpful, novel green technology. But LCA gives us an interesting perspective on that, right? What the broader impacts are of that device. And when you expand that up to the building scale, right, from a small device up to the building scale, buildings are large and highly complex systems, right? And they're typically operating in unpredictable environments with unpredictable occupants, like us. We like to open windows from time to time, right? So understanding and predicting and minimizing energy use over the full lifetime of a building becomes a highly complicated and almost wicked problem. But it's a really important one, and it's one that requires a lot of voices and a lot of perspectives, right? Because, like I said, there are a lot of stakeholders in this. So I work with faculty across disciplines to create tools that are going to make predicting energy use across a building's full life cycle more accessible, more accurate, and influential in the design of sustainable buildings. So I'm working with faculty in Aimee to develop high-fidelity thermal models that are going to help us better understand how buildings use energy, and we're going to couple those models with a novel dynamic digital design and analysis tool that I'm developing that'll help us quantify those upfront material costs and add those up with the operating costs so that designers will be armed with information that helps them understand the full impact of their design decisions. So hopefully we can influence those design decisions. And we're developing a commercializable piece of software right here at the Center for Research Computing to support that. Now, one of the ways that this tool is going to become immediately effective is in the evaluation of a novel energy conservation concept that's being developed here at Notre Dame that uses the waste heat from computers to heat buildings, and meanwhile uses the cooling that's obviously available in buildings as we feel it today to keep those pieces of equipment operating at industry standard temperatures. And this is something that happens today only by dumping a tremendous amount of energy in the form of cooling into huge centralized data centers. So what does this mean for us, right? Data centers right now, at present, they consume 3% of the electricity in this country, which is the same as 15 base power plants. So it's a lot. So we're actively testing this concept here in South Bend using a small distributed data center that's running compute jobs from Notre Dame researchers to heat the botanical garden. And the data from this is really promising for using what this is essentially a passive thermal source, data hardware, to heat a building. So we get to use one energy problem to solve another. Computers make heat. Buildings need heat. Buildings have cooling, and these pieces of hardware need cooling. But like with all energy conservation concepts, new technologies, we need to understand the broader impacts of these technologies before we deploy them at the building scale, so that we can see and we can evaluate energy use across all phases, and so we can make sure that we're not taking the impact of an energy conservation concept in one sector and shifting that impact to another. So tools that are going to help us understand the full energy impact or the energy picture are needed, so that we, the makers, certainly the consumers and the users of buildings, can understand the consequences of our decisions and the full range of impact that those decisions might have when our buildings become manifest and used in the built world. True environmental consciousness requires us to ask hard questions of some things that we assume to be true, and certainly asks us to raise our collective, let me spin through these collective expectations for the way that the built world around us is made. And that's not just true for us physical domain experts, right? When it comes to energy use in the building sector, because we all live, work, and play in them, sustainable architecture and design really is everyone's business. It's everyone's responsibility.
Professor, thank you very much. It was very good. I was thinking of buying a Kindle, but I won't now. So I can save the money and spend it on something else.